Sorry. All right, guys. Good afternoon. Today we're gonna start with a new topic, which is the topic on magnetic fields, magnetism, where you will be introduced to magnetic forces, magnetic fields, of course, and the idea behind the right-hand rule, which I will post after class. It's just a guide of how to find directions in this chapter and on the next chapter. So I want to start by introducing the similarities between electrostatics and magnetic fields. One of the first similarities is the idea of opposites and like poles. So in electrostatics, we introduced the concept of charge, and we had positive and negative charges. In this case, we have the north and south pole. But the idea is the same. Opposite poles attract, like poles repel. As you see on the screen, now instead of a charge, we have magnets. So even though there are similarities, there are some differences. So there is not really a Coulomb's law for magnetism. So when we define forces, you're going to notice the difference between how we define a magnetic force and what we need to know to find or calculate a magnetic force, and the whole idea of magnetic poles. So if you're giving a magnet, you have the north and south pole, but if you cut or if you break the magnet in half, you get two magnets, each piece with its north and south pole. Is the whole idea that magnets come always with both poles, north and south. So we haven't really found in nature, even though theoretically they might exist, but we haven't found in nature, in natural environments or even exotic environments in space, monopoles, magnetic monopoles. I mean, they are sort of predicted in the new theories in theoretical physics, but we really haven't found any evidence for them. However, they are still, we're still researching for them. So far here on Earth, when we have a magnet, we have always a north and south pole, which allow us to investigate the magnetic field. The magnetic field are lines similar to the lines that you drew for electric field. The difference is that we can map these magnetic field lines using iron fillings or a compass, as you see on the screen. So, as you know, a compass is an instrument, or it's still sort of an instrument that is used for navigation and allows you to find the north, allows you to locate the north. Why? Because of how magnetic field lines move from north to south. We can use it here on Earth because the Earth has a magnetic field. As you have seen probably several times at the homepage of the physics course in Canvas, there is an axis, the Earth has an axis, which is tilted 23.5 degrees from the vertical axis, but then around 11 degrees from the tilt, from the tilted angle, there is what we know the magnetic field axis. And we can use that to, of course, have a compass for navigation, right? The reason we have a magnetic field is because of the solid iron core at the center of the Earth and the molten material, conducting material, which is rotating at very high speeds around the center of the planet, which creates what we know as magnetic currents. And something you're going to learn between this chapter and next chapter is the whole idea of induction, right? An electric current, as we have studied in the previous chapter, can induce a magnetic field. All right. So magnetic field lines do not intersect each other like electric field lines. In the case of electric field lines, we drew them from positive to negative, as you remember. Here we go from north to south in a sort of similar fashion. And even you have U-shaped magnets, as you see right now, we still follow the same idea from north to south pole. In middle school, normally you investigate this in physical science when you place a magnet at the center of graph paper, and then you can use iron fillings, and then you can easily trace and map these magnetic field lines. So here is the illustration of the magnetic field of our planet. So as you can see, because the magnetic north is on the geographic south, and the magnetic south is at the geographic north, if we use a compass, the needle will be aligned towards the north, as it's showing in the picture. So we can locate the geographic north, taking advantage of the magnetic field lines that go from the magnetic north to the magnetic south. Okay? So even though it's tilted, it's a good way to find the north. All right? Up until the 70s, 60s, 70s, airplanes would used to use these devices for navigation in the sky, or for navigation when they were going from one point to another point in the planet, right? Nowadays we use GPSs and radars, but a lot of those devices are still built based on the logic behind the compass to locate the geographic north. So on the whiteboard, right, I summarize some of these concepts. You have the whole idea of a magnet, the magnetic field lines in a magnet, and how they go from the north to the south. All right. So that's kind of the introduction of this chapter, right? To introduce to the whole idea of magnetic fields. And that's probably the difference between magnetism and electrostatics. There are similarities for sure, but the main difference is that we introduce magnetic forces by introducing the whole idea of magnetic field. Because as you see on the equation there, the motion of a charge and later on of a current in a wire, to understand and to calculate the amount of magnetic force exerted by an external field, external constant magnetic field, is given by the equation in the case of a charge over there. The magnitude of the charge Q, the speed, the magnetic field times sine of theta. So pretty much the way we define this is by introducing the variable B, and the variable B is magnetic field. We don't use M because M is used, well, it's used for is used to label the value of a mass, but in magnetism, M is actually used to label the magnetic property of materials. So in chemistry, I believe you talk a little bit about this when you're talking about polar molecules, but we have different materials according to their magnetic properties. We have diamagnetic, paramagnetic, and ferromagnetic. So we're going to be focusing more on ferromagnetic materials, but there is a way to introduce magnetic properties and magnetism by using different materials. That's when the variable M is used, which is why for magnetic field, we use the variable B, capital B. Now, the units for magnetic field are at least a couple. We have the Tesla, of course, one of the pioneers of the study of the magnetic field and applications of magnetic fields, as you know, the Tesla coils, and also Gauss, right? There is also the unit of Gauss. which is another was another prominent scientist who contributed a lot to the study of electricity and magnetism. All right. And we have Gauss's law, of course, in electrostatics, one or the first Maxwell equation. In this chapter, you will be introduced to the other three. All right. So this equation, right, here is written in the form of magnitudes. So the magnitude of the charge, the speed, the magnitude of the field, sine of theta, where theta is the angle between the velocity vector and the magnetic field vector. So that's the thing though. Just like the electric field, the magnetic field is a vector. So you can technically introduce this equation as a vector equation. That's when the whole right-hand rule comes into account. Because in this chapter in particular, we need to introduce the third dimension. So we can have a particle moving on the plane, but then the magnetic field or the magnetic force, they might be on the dimension pointing towards you, right? So you have the X and Y, and then you have the Z axis. So we need to introduce that. So in mathematics, the way we introduce that is by introducing the cross product. And some of you should remember that because torque is defined as the level arm distance cross F, right? So torque is the momentum due to an external force, the amount of rotation, right? We also have magnetic torque, by the way. So that's your cross product. So if I was to define properly the magnetic force, that will be Q, V, velocity, cross B. That is the definition that you are going to find on the textbook. Now, this is used if you are given velocity 3J minus 2K meters per second and a magnetic field of 2I Tesla. So that's a lot, but still. So if you're given values like that, well, you know that the charge can be is a constant, it's a numerical value. So you have to multiply this. That's not the scope of the course, although you should know how to do this. But that's not what you're going to be seeing. We're looking at the magnitude. So the magnitude of the magnetic force is Q, or the magnitude of Q if you want to write it like that, and the magnitude of this cross product, right? And the magnitude of this cross product is, well, V, B, sine theta. That's how you define the magnitude of a cross product multiplication. If you remember, the dot product of vectors is defined as magnitude of A, magnitude of V, cosine theta, right? That's calculus one. Calculus one, yeah. So that's all pre-calculus. It's pre-calculus. That is a definition of cross product. So that's where that equation comes from. All right. Okay. So why is this important? Because V cross B means vectors that may be perpendicular. If you have V and B perpendicular like this, the force has to be perpendicular to these two vectors. So that's when you have a vector that may be like this. And if you think about it, right, what I'm showing you right now there is your X, Y, and Z axis. In fact, in mathematics, that's how you define the Z axis. So you have an axis like that, and then you have like that, right? You have the x-axis, you have the y-axis, and then you have the z-axis. So the way you define, they are all perpendicular. You use the right-hand rule like this, x cross y give you z. So that's what we're gonna use for the right-hand rule, all right? So the right-hand rule is the whole concept and idea to find the direction of the magnetic force. And there are a few that we're going to introduce between this chapter and the next chapter of induction. The first right-hand rule is the way we're going to find the direction of the magnetic force due to a moving charge. So let's suppose you have a positive charge moving to the east from left to right. And you have a magnetic field going up. When we did electric fields, the charge, if it's positive, will move on the direction of the electric field. Now with magnetic fields, because of these definitions, right? It doesn't. The magnetic force is perpendicular to both the velocity and the magnetic field. So how do we find this magnetic field direction? Well, you're gonna use your right hand and you're gonna use your 4 fingers on the direction of the velocity, all right? And then you're gonna curl your fingers on the direction of the magnetic field. So if the magnetic field is going up, then you're gonna place your hand like that. So you can curl your fingers up, and then your thumb will tell you the direction of the force. So clearly, the force is out of the page, so it's coming towards you. And that will be the way we use the right-hand rule for a moving charge. Now, there are different variations, and the first 2 questions in assignment 7 are about right-hand rule. So that's why I want to do a few. For example, let's take a look at the other one here, right? You have now the velocity going up and the magnetic field going to the right. Be very careful with using the left hand by mistake. For example, if I were to use the left hand by mistake on the first example, it will give me the opposite direction. So be careful with that. Always use the right hand rule or the right hand. If the velocity is going up, so your fingers should point upwards. Now, how do you know if it's like this, or like this? It depends on the direction of the field. The field is going to the right. So you're gonna place your hand like this, right? And then you're gonna curl your fingers on the direction of the field, like that. And then your thumb is into the page. So that's why this is into a page. So a few labels. That means out of the page. That means into a page. It's like an arrow, the tip of the arrow and the tail of the arrow. All right. Now, just as a note, if the angle is 90 degrees, if the velocity and the magnetic field are making 90 degrees, that's when you find the maximum magnetic force, because the sine of 90 is 1. So QVD will be the equation to use when the magnetic field and the velocity vector make 90 degrees. Okay, let's do a few examples of right-hand rule. And let's actually take a look at what happens if there are angles, like for example in this case. So let's suppose you have a charge, positive, going downwards, and you have a field going like this. All right. And that's the angle theta. In fact, normally they draw several lines just to show you this. So how do I use the right-hand rule in this situation? Well, looking at the equation, if the magnetic field and the velocity are parallel, the sine of, well, the angle is 0 degrees. So the sine of 0 is 0. That means that there is no force. So the way you can think about it, in this case, is that this B has two components. It has the vertical and it has the horizontal. You can put this Bx, By. Now, this one is parallel to V. So we disregard this one for the direction, for the right-hand rule. Right-hand rule. But then we use Vx, which is going to the right. V is going down, Vx is going to the right. So I'm going to place my hand like this. Why? Because the velocity is going down and the magnetic field is going to the right. So that means that my thumb is pointing towards you, right? Down, right, there. So the magnetic force is out of the page in this case. So here we have the magnetic force out of the page, like that. All right. So you're doing. That's the first right-hand rule. Now, what happens if the charge is negative? Well, let's show you that. Here's another example. If the charge is negative, you use the same rule. Let's suppose Q is going to the right again, like that. But now I'm gonna say that the field is going downwards. All right. Like that. And the charge is negative, of course. If you want to find the magnetic force in this case, we are going to, for now, ignore the charge sign. We want to use like this. But now the field is going down. So I place my hand like this, not like this. It's going down. So like this, down the field, and my thumb is going into the page. But wait a second now. The charge is negative. So it's supposed to go into the page. But because the charge is negative, it goes on the other direction. So in this case, it also goes out of the page. All right. That's the whole idea behind right-hand rule for a moving charge. So that'll be the same idea for electric current. If you think about it, electric current are moving carriers, moving electrons, or a flow of charge. So it should be the same. So that's the kind of the introduction of this first concept, right? The thing about magnetic fields or magnetic forces is that there are several applications. One of the major applications is the application on cyclotron radiation or a particle accelerator, right? As you know, we build particle accelerators in the shape of a donut going in a circumference, for example, the LHC in Switzerland. And why does it go like that? Because when we accelerate protons, which we do because they are very massive, and when they collide, they can emit large amounts of energy, which is the aim of that experiment, right? But the reason we do it like that is because of how charge behaves in a magnetic field. So let's show you the application of magnetic forces applied on a moving charge. Using right-hand rule, of course. Let's suppose you are given a positive charge here. And the charge is moving towards the east with some velocity. Now, the charge is going to enter a region where there is a magnetic field into the page. Notice how I label the magnetic field. So these X's, or yeah, these X's are to show you that the magnetic field is into the page in this region. All right. So for now, let's just put here B into the page. So as the charge enters a region, this was going to happen. Maybe a bit more pronounced. Like that. Why? Well, let's suppose the charge is here. And is moving like this, right? If I apply the right-hand rule, velocity, field equals up. So there is a magnetic force going upwards. So the charge is deflected up. What about here? Why does it do that? Because if the charge is here and it's now moving like this, the velocity is up into the page. There is a force now like this. So it's going to be deflected like that. And then, of course, why does it go in a loop? Because if you have a charge there, and now the charge is like this, you have the velocity now like this, right? Like that. And then into the page, it's going down. It goes down. And eventually, here, you have the velocity and the magnetic force like this. All right, a few things about this. The path is circular and V is constant. So it's a circular motion at constant rate. So there is going to be period. Furthermore, there is some radius here. If it's going at a circular, if it's going in a circular motion, this magnetic force, we know what it is. That magnetic force is equal to what? It's equal to the centripetal force, which is the force that is always acting, pointing towards the center of the path. Magnitude-wise, all right? The magnetic force, all right. The velocity, in this case, in every instant, is perpendicular to the field. Always. The field is going to the page, and the velocity is like this, like this, like this. So it's always making 90 degrees. That means that we can use that equation for magnetic force, QVB. So here, QVB, what's the equation for centripetal force? Well, mv squared divided by r. So we can find a relationship between charge and mass. We call that the mass charge ratio. V. So we can put it here. The radius of the loop is equal to mass times velocity over Q times magnetic field. This is an important equation as an application of the motion of a charge in a magnetic field. As I mentioned before, the speed is constant. So if the speed is constant, there is period. How do you find the period of a particle or a mass moving in a circular motion? It is the length of the path divided by the speed. The period is defined as the time for one revolution. 2 pi over omega. Pretty sure you saw that equation. But we can define it by using this equation for radius. So I have the equation for radius there. We define capital T as period. So this is period. In seconds. So period will be 2 pi r. That's the length of one revolution. That's the equation for circumference, right? Arc length divided by v, which is the speed. Well, r over v, you can get it from here. R over v is m over qv. If I combine both equations, the period is 2 pi m over qv. That's the equation for period. All right. So a few equations so far. These two are applications for the electric force in a charge moving in a perpendicular field. And then you have the definition of magnetic force due to a charge. I want to introduce now well, I want to show you a few slides as well. And then I want to introduce the idea of current, just to see, so you can see the similarities. And then we can do a few examples. All right. Now, keep in mind a few things though. We have defined magnetic force in most of the equations and applications by using the magnetic field. So eventually, and by the way, in all of these applications, the magnetic field is uniform. Eventually, we're going to go into variations of the field. All right. For now, the magnetic field is uniform, so it's constant, and it's an external field. Probably today, later, we're going to introduce the whole idea of how magnetic fields are produced. That will introduce the second right-hand rule. All right. I'm pretty sure you already took your notes, so let's go here. So in the slides, you can find this, which I already explained, the magnitude of the magnetic force, the definition of field, the units for field, Teslas, that's what we're going to be using the most. Your right-hand rule there for a moving charge, okay? The definition, the vector definition of magnetic force, and your application for the motion of a particle in a perpendicular magnetic field. All right, so the slides are basically the complement of everything, of course. A few things, by the way, before we move on, I want to show you. If you guys go to modules in this particular chapter, by the way, here's a few recordings for this same topic. This chapter has these sample solutions for a few problems that are similar to the ones in Cengage. Now, this particular module has that because these solutions, I wrote them right before we unfortunately went online. This is going to be 3 years ago now. So around that time, we were about to start this chapter, so I made all this. So make sure that you, and I explain here right-hand rule and a few of the problems. So for example, here, you see, kind of what we just did. So look at those examples if you're finding difficulties. That's something extra in this module, all right? And here is what I was talking about with the mass spectrometers and particle accelerators. We use this for ions of different masses to kind of analyze their mass charge properties. As you can see, depending on the ion and depending on their masses, they will have circles of different radii. So there is a problem on the assignment where you have to do, and if I have time, I will do it today, if not, for sure tomorrow, where you have to apply some of this in a mass spectrometer. And the nice thing about that example is that it also combines electric fields. Because as you know, magnetic fields are not the only fields acting in particle accelerators. If we have capacitors, for sure we're going to have electric fields. So they also play a role when we are trying to deflect particles in these environments. Here they show you what happens when the velocity of the particle is not exactly perpendicular. If the velocity of the particle enter the region is not perpendicular, you still break into components. The perpendicular component is the one responsible for the circular path, as you just saw on the board. But what about the parallel component? Because the parallel component is not affected by the field, then the particle will still move. But think about it. If there is no force acting on if there is no magnetic force acting due to the parallel component, then there is no acceleration. If there is no acceleration, then the particle moves horizontally at a constant rate. Okay, so pretty much the way you can see it is that the distances between each loop here is due to one period. So after one period, one here. After another period, because the time it takes to go from one loop to another loop is one period. Right? That's the concept of constant rate. Distance equal to speed times time. All right. All right. So are there any questions about this, by the way? All right. So give me a second here. Magnetic forces for a current carrying wire. Let me show you the slides there for a bit. I want you guys to take notes of that while I raise the whiteboard. As you expect, the idea behind the magnetic force due to a wire is going to be very similar to the one due to a moving charge. Why? Because of our definition of current. Current is the flow of charge. So let's write the equations here. All right. So that's for a moving charge, right? So when we define current, we had a conductor, and you remember I said that the way the convention works is that it's assumed that you have positive carriers traveling at this drift velocity, right? Now, in this wire, you have a cross-sectional area, and the carriers are moving at some velocity going through some volume. It depends on the delta X. All right. So then we define current as the density of carriers, charge, drift velocity times the area. Right? The area here. Well, look at this and look at this. Now we know that the units for this density are number of particles per volume. Now, area over volume is basically proportional to basically length. Is 1 over length. Or in his case, 1 over delta x. So that's where your delta x will appear, the length of the wire. So if I were to define here, QVD is the current over density times area. Because of this is basically the same as IL. So I put I in there. And the magnetic force will be IL B sine theta, which is the equation that you had on the slides. So now, for a current wire, that's the equation for the magnetic force. Now it's not about charge or velocity, it's about current and the length of the wire. And this starts bringing a few applications, magnetic torque, and we can use that for, or to explain a little bit of the physics of certain conductors embedded in magnetic fields. All right. So let's not forget, L is the length of the wire. All right. You know what I is, you know what B is. And theta is the angle between the current and the field. So how do you use right-hand rule for this? Well, it's the same. The way you use right-hand rule for that, in that case, if you're giving a current like this, you are giving a field, let's suppose it's going upwards. If you have that, what's the direction of the magnetic force? Now your 4 fingers are going to be on the direction of the current. And you're going to place your hand depending on the direction of the field. The field is going upwards. So you want to place it like this. Upwards towards you. So the magnetic force is out of the page. Right-hand rule for forces. All right, and that's the equation for it. All right, so let's do a few examples. For that, I'm gonna use the guide that you can find in modules. I have it here already. And if you guys wanna write it down, I'm gonna share my screen. I'll do problem 5 and problem 6. All right. In fact, both of those problems are similar to what you could find in a final exam. Same level. Number 5, an electron moving perpendicular to a field, uniform magnetic field of 0.22 Teslas, moves in a circle with a speed of 1.5 times 10 to the 7 meters per second. What is the radius of the circle? Well, we just have to apply the equation. You just have to be careful with the units, right? So write it down while I do it here on the board. So we have the equation for that problem is R equals to mv over qb. So if we write the data, the magnetic field is 0.22 Teslas. The speed is 1.5 times 10 to the 7 meters per second. And they tell you that it's an electron, right? So let's stop this for now. So that's the data given in the problem. The charge of the electron magnitude is 1.60 coulombs. Mass of the electron 9.11. Okay, a few things, by the way. You're gonna notice that another difference between magnetic fields and electric fields is that magnetic fields are generally very weak. So we're gonna find very small values for fields, magnetic fields. And that's gonna make sense once we introduce the whole idea of an electromagnetic wave, how they are related to one another, the electric field and magnetic field. Now, another thing I want to point out right now is that when I was grading the exam yesterday, and then I went and looked at the assignments, I noticed that some of the errors from some of you was how to handle these equations with numbers like this. The units, the prefixes, conversion of units. That's one of the advantages of doing the sandwich, that it allows you to practice all these situations, right? So the correlation is as follows. If you are doing the assignments, at least, you know, half of them, half of one, half of two, half of three, or you are trying to keep up with the assignments, you are going to be doing good in the exams. So I will strongly suggest that that's the way you can pick up. All right? By practicing, like after class, try to do at least the first 4 problems of assignment 7. In fact, you should be able to do all assignment 7 after today. But anyway, so 19 plus 7 is 26, minus 31 is -5. So we do 9.11 times 1.5 divided by 1.60 divided again by 0.22 multiplied by 10 to the -5. Right? So let's see what we get. And you see that 10 to the -5 in there. So if I were to do 9.11 times 1.5 divided by 1.6 divided by 0.22, I get 39. I'm right to 39. But you get 39 times 10 to the -5 meters. In exam, that's okay. But what happens in the final exam or multiple choice exams is that they give you options like the ones in here, right? 3.9 millimeters or 0.30, it's all in millimeters. So we have to convert this in millimeters. Millimeters is 10 to a negative 3. So you multiply this by 100 to make this 10 to a negative 3. So you divide this by 100, right? If you do that, this becomes 0.39 millimeters. And that's the answer. The answer D. All right. So that would be the radius of an electron.
Wait, Professor. Where does the 10 to the power negative 5 drop?
This
Yeah.
10 to a negative 19 goes up a step.
Yeah, no. For the final question, you say 39 times 10 to a negative 5. Shouldn't 0.39 millimeter times 10 to the power negative 5 as well?
Well, this is 39, right?
Yeah, 39 times 10 to the power negative 5. Yeah, I get that. That's in meter. So you divide by 100.
Multiply by 100. And you divide by 100 here.
Okay.
So 0.39. And then 10 to a negative 5 times 100 is 10 to a negative 3. And 10 to a negative 3 is millimeter.
Oh, okay.
All right. So those are little things that if you don't have it clear, you need to practice it, because at this level, guys, that should not be rocket science. So I know you do that in high school. I teach in high school, so I know you guys do that. It's just that, well, as I tell my students, right, these little things come back. Millimeters, meters, centimeters, kilometers, megameters, nanometers. Again, if you leave that in an exam, that's okay. In a multiple choice, you're going to be given options like that. The question is easy. It's just applying that. But they're going to try to trick you with the answers. All right? So that's why I want you guys to start practicing the same gauge. Because in the same gauge, sometimes they request to write an answer in microseconds, in millimeters, in whatever. So practice your unit conversions. All right? As real life, when you go shopping, right? Home Depot. I don't know if they do this now, but sometimes you have to do conversions from millimeters to meters, like depending on what you're buying. So you use these things in real life. Okay. Anyway, so that's a way to do this problem, all right? Number 6. Let's see. There. An electron moves with a speed of 8 times 10 to the 6 on the x-axis and enters a region where the field is 2.5, that's high, and an angle of 60 degrees with respect to the positive x-axis on the x and y plane. Calculate the magnitude of the magnetic force. All right, so let's do that. I'll do it here. Another easy problem, applying the formula for magnetic field due to a moving charge. So what you are telling, it says calculate the magnetic force, electron moving with a speed of 8 times 10 to the 6 meters per second in the positive x direction. And you have the field of magnitude 2.5 teslas at 60 degrees with the x-axis, right? So the data is given like that. And it's an electron, so we're going to find them. If they ask you for the magnitude, you don't have to worry about the vector. Yeah, they only ask you for the magnitude. So everything is in SI units. Q is an equation. Oh, it's not that. So the equation is 1.6 times 10 to the negative 19 Q V. And sine of theta, the angle between the velocity and the magnetic field, which is 60 degrees. There you are. That's very good. All right. $23.2. 32 times 10 to the negative 13 sine of 60. That's 1.7, no, that's 0.86. This is around 28 times 10 to a negative 13. But as you can see on the answers in there, it's with 10 to a negative 12 exponent. So how do I change this to negative 12? I divide it by 10, multiply by 10. So 2.8 times 10 to the negative 12. All right. Any questions about these examples? Okay, let's do a right-hand rule here. There. So this is a theoretical question, right? It gives you an electron moving to the right, as shown in the figure, and then there is a magnetic field. You don't know the direction. Oh wait, no, yeah, it says that it's a magnetic field pointing out of the page. What will be the path of the electron? So, let's see if I can do it here. You have the how do I change this? So you have an electron, right? And if the field is pointing out of the page, that means that there is a field which is like this, pointing towards you. And the electron, which is a negative charge, is moving from left to right, like that. So the right-hand rule states that your 4 fingers are gonna go towards the right, no, towards the right, and you're gonna be pointing your fingers like that. Why? Because the field is going out of the page. So you put your hand like this. It's going like this, and then your fingers have to go out of the page. All right, don't do it like this. Well, first of all, the electron is going like that. Don't use your left hand. Be careful. So you want to do it like this. Do it like this. So that means it should go down, right? But remember, it will go down if the charge was positive. But in the problem, it's an electron, so it goes up. So if we go back to this, the electron will go on path A. All right. That's what I was saying. It's a good way to practice right-hand rules. Here they give you an electron. And by the way, this is interesting, right? You can have magnetic fields that are in or out of the page as well. All right. You're going to see that a lot in the next chapter, by the way. A lot of situations where the fields are in or out of the page. All right. Okay, let's see now. Okay, this is an interesting problem as well. Now you're giving a wire. So now we're going to current. You have a wire of that shape with a current of 2 amperes, and there is a field in this direction with magnitude 0.75 Teslas. What are the magnitude and direction, so here they ask you for direction as well, of the force acting on this section, on AB. All right, so write that down because I'm gonna do it on the board, okay? So here we're going to use the equation for a wire with a current, but we have an M shape. All right, so we have AB, 10 centimeters, current of 2 amperes. But the magnetic field is going at an angle of 45, right? Like that. And the field is 0.75. Teslas. So find the force acting on AB. So what's the magnitude and direction at AB, segment AB? Okay, because you have a current, you have to use the magnitude of the magnetic force, I, L, B, sine of theta. What about the direction? The direction comes from right-hand rule. So let's do the direction first. B is in all this region, making an angle of 45 degrees with the horizontal. That makes it easy to find the angle between the magnetic field and the segments here. They are parallel, horizontal, so the field here will be like this, right? Making an angle of 45 degrees. Because that's what happens, then we know that the angle theta is 45 degrees. The value of the current is 2. The length is 10 centimeters in meters, 0.1 meter, and B is 0.75. So we have all the values to find the magnitude. What about the direction? So the current is going from left to right, but the field is going at an angle. But wait, what did I say before? If the field and the current are parallel, or if the field and the speed of the charge are parallel, right? There is no force. There is no magnetic force. So this component doesn't exert any force. It's this component here. So you have the field going like that, you can break into components, right? One going like that, one going like that. The one going up is the one that exerts a magnetic force. So you have the current like that, field going up, the magnetic force is out of the page. So that's the direction, out of the page. There you are. What about this? I is 2, L is 0.1, B is 0.75, sine of 45, root 2 divided by 2. And that's how you solve this problem. Any questions? Sí. Point 11, right? The answer is 0.11 newtons. Okay. So as you have seen in these examples, it's very you apply the equation. You just have to be careful with the right-hand rule in some cases, with the units, but it's not that complicated. All right, at least at the beginning, it shouldn't. You are going to be given the uniform field, and then you just have to be careful again with the units, with the right-hand rule if they ask you for direction. But let's keep looking at what other applications can we find. So we already did this. I want to use the slides for this because this topic or this section is important, but it's normally not really evaluated. But you need to know it because this will explain, or we still use this when we talk about induction and motors. All right. But it's the whole idea of the torque due to a uniform magnetic field in a current loop. So let's suppose you're given that situation. You have a current loop, rectangular. The field is going from left to right. And as you know, the current is going clockwise, right? Like this. So we can apply right-hand rule to find the direction of the force on each of these sections. In fact, they give you the force here and here. How do you know it's out of the page? Well, think about it. If the force is going down and the field is going from left to right, you're going out of the page. Now the current now goes up on the other side of the loop, up, like this, up, but the field is going from left to right into a page. So that's how they find the directions of that. Now, why, or can somebody tell me, if you've been paying attention, right? Why there is no force here and here?
Because it's parallel to the magnetic field.
So if the angle is 0 degrees, then there is no force. So there is only force here and here. Now, every wire, even though it might be hollow, or is hollow, there is still a center of gravity, and there is an axis of rotation, which is normally either this axis of symmetry or you have the other axis of symmetry, right? But because there are forces in here, we draw this one, the one in dotted line. So that's our axis of rotation. Think and try to remember what you guys talk about in torque at the end or towards the end of physics 1. I'm sure you guys were given the example of a door and the fixed axis of rotation, right? If you have a door and you are opening and closing it, you are only, or you are exerting a force on one of the extremes opposite to the axis of rotation. Furthermore, the farther you are from the axis of rotation, the easier it is to produce the rotation, which is measured as a moment, the moment due to a force. So now here we have two forces, but they both are going in opposite directions. And we have that axis of rotation. So what do you think is going to happen if we let it go? Well, it's going to start to rotate. And if it's rotating, it's basically going to do this, right? If that's your loop, it's going to do this, right? Like this. So that's due to the magnetic forces. That's, or we quantify that by calculating the torque respect of the axis of symmetry, which is the one in the center here, right? If this is length W, this is W half. That's where the axis of symmetry is located. We know H, and each force is acting here and here. Into the page, out of the page, maybe, right? Or like this, out into the page. Now, what's the definition of torque? The magnitude is the amount of force, right? If I have my axis here, multiplied by the distance. So if the force is acting here, the distance between the force and the rotational, the pivot, like that. But in this case, the axis is going through the center. And there are two forces. So the torque will be written like this. IHB, where does the IHB come? That's the force. ILB now is, instead of L, is H. Why there is no sign of theta? Because theta is 90 degrees, right? Look at this. What's the angle between this side and the angle and the magnetic field? 90 degrees here, 90 degrees here, sine of 91. So that's the force times distance, W half. Well, there are two forces. So there you are. Now, IHBW, IHBW. But what's H times W? Area. So the torque, the magnetic torque is given by this equation. But let me be honest with you guys. That's a very simplified equation for torque. You know why? Because first of all, we're assuming that the loop is parallel to the field, right? Or at least two of the sides are parallel to the field. Secondly, we're assuming that the loop is made of one wire. If you have ever opened a computer, let me show you that. Like the case of a computer, you will find that around the fan, there are what we know as coils. Let me show you a picture actually here. You probably have seen this before in real life. Coils like this, or like a solenoid, like copper wires or things like this. So you see the amount of turns. Each turn increases the amount of torque. We call that the number of loops or turns, and we label it with a variable N, capital N. So that's another factor that we have to take into account. The area, well, that's taking into account, the current is taking into account, but again, we haven't taken into account the number of turns and if there's an angle. So how do we take into account both of those? Well, let's imagine there is an angle in between the wire and the angle and the magnetic field, let's suppose the angle is theta. But what angle theta is this? If you have a wire like this, or a plane, there is always this idea of the normal. That is the normal to the plane here. All right. If the field is going like this, the angle is 90 degrees. But let's suppose the loop is tilted. So now there is an angle there, right? There. But be careful though. It's not the angle that you are seeing there. The angle that we are interested is the angle between my wire and this. And what's this? That's the normal to the loop. If the loop is like this, the normal is like this. So I want this and this angle here. That's the angle I want. That's what the picture here is showing you. So that changes the distance between the axis and the action of the force. Instead of being W half, parallel lines, theta, 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 right? Or you can think about this as this is 90 minus theta, right? Because they have to add up to 90 here. This is theta and this is theta. So if this is theta and this is W half, this is W half sine theta. So now that's the distance. That's where your angle comes. And we use that as a distance, and we get the equation IAB sine theta. And if we include the number of loops or number of turns, that's your equation of torque. So that's the equation you want to write down. The general equation for the torque exerted on a loop with area A with number of turns N. All right. You might not be tested this, but we're still going to use this when we talk about generators and motors, because that's kind of why that's a way to quantify rotation due to external fields. All right. And you know, rotation gives you kinetic energy, and kinetic energy can be used for what? To produce electrical energy. Basically, the physics behind a hydroelectric dam, right? Which is the whole idea behind induction in the next chapter. The units for torque, as you know from physics 1, Newton's meters, is not joules, because the concept is different. It's the level arm multiplied by the force. That's the magnitude, but remember, torque is a vector perpendicular to the rotational axis, all right? So, or the plane of rotation. Any questions about this? I mean, this is the proof. You think about it. That's the question there. And there you are. So let's see where we apply this, right? We apply this in a few instruments in the lab. One of those is the galvanometer. So the galvanometer is a similar instrument to the one that all of you have used, which is the ammeter. The ammeter in a lab allows you to find the current by having a scale and a needle, right? Everybody knows that. Everybody's using that. Good. But what about the galvanometer? The galvanometer uses a coil and a magnet, or a pair of magnets. You have the magnetic field going from north to south, like that. And you have a conductor and a coil in between. Because of what we just explained, when there is a uniform field and there is a coil going, and there's a field going through a coil with area A, there's going to be a magnetic torque. And what does the torque do? The torque measures rotation. So as soon as you activate the field through the coil, there's going to be rotation. That rotation can make the needle move. But at what degree? How does the needle move? Well, according to the current, right? The more current, the more torque. So the needle will move the most if there is more current. Well, there you go. That's how you can measure current. You can measure current by the amount of rotation. The amount of rotation will move the needle to 1 ampere, 2 amperes, etc., etc. You know why what's the advantage of using a galvanometer? Galvanometers normally can measure also negative currents. And as you know from the lab, ammeters, analog ammeters do not always measure or never measure negative currents, right? Digital ones do. Digital ammeters, multimeters, they use that. But a galvanometer can go from negative currents to positive currents. Why is that important? Because we have the whole idea of the direction of the current, which is going to be important now that we start talking about fields. All right. So I will try to do an example of torque tomorrow. What I want to introduce now is the second or third, Maxwell equation, all right, which is the one related to the calculation and direction of magnetic fields, all right? Now, so far, we have introduced magnetic forces. We have looked at some applications, such as the motion of a charge in a magnetic field, currents in magnetic field, magnetic torque. But in all of these equations, we need the value of the field. So what is field? How do we produce a magnetic field? Well, I said at the beginning of class that the Earth has a magnetic field due to the electric currents in the molten core of the Earth that is rotating around the iron core of our planet. In the case of the Jovian planets, right, Jupiter, Saturn, I mean, if you have taken an astronomy course, that's good, but if you haven't, something that you should know is that those planets are made of gas, and they don't really have a surface. They have a small core made of rock. So how do they produce much stronger magnetic fields than our planet? Because they have liquid metallic hydrogen in where the mantle will be in our planet. So instead of having a mantle like us, rocky mantle, they have in between the upper and the core, the upper layer and the core, they have like a they have a layer of liquid metallic hydrogen, which is rotating. So that's a conducting material. And because it's moving, it produces largest amounts of current that induces or creates this magnetic field. So that's the key. The key to understand magnetic fields is to understand or is to observe electric currents. And this is easily, or this can be easily tested in labs or even in at home, right? You can use a magnetometer, which is a device that can measure the amount of magnetic field in certain regions, right? So if you have a cable, maybe the power cable from your computer or any appliance, you can measure the amount of magnetic field due to the current flowing in that wire. So here we have, if we place a wire and then we place, like I did before with the iron fillings around the magnet, but now around a wire, that's what you see. You see the iron fillings making a circular shape around the conductor. Now let's replace those iron fillings with compasses. And look at the needle of the compass. As it goes around the conductor, the needle moves, always pointing, pointing towards the north first and then pointing towards the south, depending on when you are, depending where it's located. So the needle is moving because there is a field that is moving it. So then there is a magnetic field due to that current. All right, let's explain the right-hand rule for this. I mean, you have an explanation there, but here is the second right-hand rule, which is the right-hand rule for magnetic fields. When you are solving problems and trying to find directions, make sure you read carefully what the problem is asking you. If it's talking or asking you about direction of magnetic field, you have to use this rule. And there are a few differences. We're given a conductor, normally a long conductor, carrying a current I. You saw in the slides that the compasses or the iron fillings go in a circle. That's not a coincidence. You're gonna use now your thumb and you're gonna place it in the direction of the current. And you're gonna rotate your fingers around. That gives you the direction of the field. So you're gonna do it like this. It goes into the page here. And then goes out of the page here. That's my magnetic field. Again, you have to think three-dimensionally. All right? Is that conductor is this. Into the page, out of the page. Into the page, out of the page. That's the right-hand rule. For fields. And as I said, there are different variations. So let's do a couple and then let's introduce Ampere's law. Now, I want to be honest though. Ampere's law is what you have to learn, of course, but Ampere's law is a simplification of a general equation to compute magnetic fields. The person we owe the calculation of magnetic fields is known as Biot-Savart, who gave this very, I want to be honest, complicated formula that takes into account this, the direction of the current and the direction of the magnetic the direction of the conductor and the current in a given region. All right, but let's see. If you're given a wire now like this, how do I find the direction of the field now? Now it's about finding the direction of the magnetic fields. You see the wire is going like that. So now my thumb is going to go like this, right? Like that. And then I'm going to go and do my fingers like this. So this is going to go down, but then up. Down, up. Down, and then up. That's where it goes. So it goes into the page at the bottom. And then when it goes up here towards you, out of the page. That's my magnetic field direction. All right. So this is the right-hand rule for fields. Are there any questions, by the way? Okay, so let's put something. Okay, so how do I find the magnetic field? Well, the definition of field is actually quite complicated. That's what you will find in textbooks. We're going to simplify this, don't worry, but that's what you will find on any physics textbook, right? It depends on the current, it depends on this I'm going to introduce right now, and it depends on the geometry of the conductor. And look at this, right? It's a cross multiplication with the distance to the given point where you want to find the field divided by the cube of that. So that's vectors and that's the magnitude. So it becomes quite messy, by the way. Well, it depends on the conductor, right? Okay, that's Biot-Savart law. That's a Biot-Savart law. And why am I showing you this? Because of that mu naught. What is this mu naught? Mu naught is, you remember E naught in electrostatics, or yeah, in electrostatics, mu naught is now the magnetic permittivity or permeability of free space. That's what it is. What does that mean? It tells you how good is the environment, vacuum, air, or any other environment, a conductor, for example, or an insulator, or a paramagnetic, diamagnetic, right? Depending on the type of materials, it tells you how good magnetic fields can flow in that given region. And what's the value of it? That's a constant. E naught is a fundamental constant for electrostatics. Mu naught is the fundamental constant for magnetic fields or for the study of magnetism. And the value of it mu naught is defined as 4 pi times 10 to the negative 7 Teslas meter per ampere. That's the value of mu naught. All right. Now, calculating magnetic fields using that is useful, but we can simplify this equation for what we are interested in this course, which are long conductors and symmetrical conductors like solenoids and toroids, or even circular loops. All of them have symmetry. In the case of a long conductor, right, we can find, because you see this circular shape, the circle is the perfect symmetrical shape. So we can find the magnetic field at some distance r. That's when we introduce the whole Ampere's law. Ampere's law takes this equation and simplifies it a little bit. How? By saying that the linear integral of the magnetic field is equal to the magnetic permeability times the current on the wire. All right. Most of you are going to do those type of integrals later in mathematics, right? That's calculus 3 in some cases. but it's basically the amount of field in one length, right? And what's one length in this case? So the linear integral is basically integrating the field through one circumference. So I know what's one circumference. One circumference is 2 pi r. So I can simplify this by B times 2 pi r equals to mu naught I. Well, the magnetic field for a long conductor is mu naught I over 2 pi r Teslas. That's the equation you need to know. Let's put here magnetic field due to a long conductor. All right. So that is simplified to this. So it makes sense. As the R increases, as the distance between the conductor increases, the field decreases as 1 over R. All right. What are the assumptions here? That the current is constant, which for now is okay. And that the field at a given point is also constant. And it decreases as you go farther from the conductor. All right. So that's how you find the directions. That's how you find the magnitude. All right. So we have time to do one example before we finish class. I will do another one tomorrow because we want to be in person. And then I'll do the mass spectrometer as well tomorrow at the beginning of class. All right. So this introduces another set of problems. And this now is touching assignment 8, by the way. In assignment 8, you start finding problems with fields. Let me show you the typical problem you can get in this situation. So I'm going to leave this in here. And let's show you what you can get in an exam. You can be given, so let's do example here. And let's say you have 2 wires. One here, carrying 4 amperes, and one here going down, carrying 6 amperes. The distance between these 2 cables is 60 centimeters. And you can be asked to find the magnetic field at any point. Let's suppose they want you to find the magnetic field here, which is at the midpoint. So find the magnetic field vector at point P. Similar to what we did in electrostatics, right? Remember electric fields, now in magnetic fields. So you want to find the magnitude and direction. This is magnitude and direction. All right. So we want to find the magnitude and direction of the magnetic field in the midpoint between the wires. One is going up 4 amperes, one is going down 6 amperes. We have to do it step by step. First of all, let's find the magnetic field direction due to 4 amperes. So remember this, like that. I'm doing for 4 now, and then it goes like this. So it's going to go into, out. into a page, out of the page here. And P is gonna go into a page. That's B1 due to 4 amperes. What about due to 6 amperes? It's going down. So I do my right hand rule. It's going into a page here, out of the page. Into a page, out of the page. So also for this, it's going into a page. B2. Why do I need to do that? Because now I know that they both are going into a page. So I have to add their magnitudes. Now let's find the magnitudes. To find the magnitudes, we use this equation. So B1 magnitude will be the magnetic field. If this is 60, this is 30 centimeters, 30 centimeters. So given that the equation will be mu naught times 4 over 2 pi. What's R? The distance 30, but 30.3. So 0.3. So let's replace the value of mu naught. 4 pi 10 to a negative 7 times 4 over 2 pi 0.3. Pi, half 1, half 2, 1, half 2, 8. 8 divided by 3. So 8 over 3 times 10 to a negative 6. That's approximately 2.7 times 10 to a negative 6 teslas. That's B1. All right. And now B2. Again, using this, B2 will be 4 pi, like that, multiply now by 6, divided by 2 pi. What's the distance? The same. It's the middle point. Pi, half 1, half 2. 12 divided by 3, 4 times 10 to a negative 6. We know that it's going into the page, So the magnetic field at P is that plus that. 6.7 times 10 to a negative 6 teslas, and you can write here into a page. Very well. Tomorrow I'll do one on finding on each sides and a problem on the mass spectrometer. So basically, we've done almost all chapter 18 and part of 19. We have to introduce solenoids tomorrow, application of solenoids, examples, and I will introduce induction. So I posted a schedule for the quizzes, guys, or for the quiz in the next exam. The third quiz will be via WebAssign, so will be posted in WebAssign Tuesday. All right, we'll post it on Tuesday after class. And then the take-home exam will be given to you guys on Thursday next week. It will be all about magnetic fields, magnetic forces, induction, and inductance. and most likely RLC circuits as well. We'll see what we get to that point on that.
Wait, Professor, so for the test next week, would magnesium be on it?
This, yes, for the quiz, yes. Yeah.
No, assignment 9 and 10, would that be on the test?
The test normally covers assignments 7, 8, 9, and 10.
7, 8, 9, and 10. Okay, so test 3 will be 11 to 15, right? Or,
Essentially, yeah.
okay, got it.
Okay, let me finish taking the attendance and then I'll let you guys go.
Professor, I have a question about the lab that's due tonight.
Yeah.